In our next section, we're going to look at the carrier supporting carrier, or the CSC feature, which is used for what's sometimes referred to as hierarchical MPLS layer 3 VPNs, when one L3 VPN provider is using another L3 VPN provider in order to get long distance transport. Now, specifically, this feature is defined in RFC 4364, where we referenced previously the inter-AS options, where we define option A, B, and C. And this is in section 9, which they call the carrier's carrier. So if we look at specifically, it is number 4364. 4364. And then it's section 9, which is carrier's carrier. It says that sometimes a VPN may actually be the network of an ISP with its own peering and routing policies. And the VPN, like these, can also obtain backbone service from another service provider. The carrier's carrier essentially is the same method described in this document. However, it's necessary in this case that the CE routers support MPLS. Okay, so basically what this feature is going to be for is when one provider is transiting another one, but the link between them has to be MPLS aware in order to solve an LSP problem of the devices in the core carrier, what's sometimes referred to as the backbone carrier. Now, in terms of a real use case, it is not as really common to use this as a layer 2 VPN would be, that if you have a provider in New York that wants to attach to Los Angeles, they would typically just buy layer 2 transit from another provider, like a point-to-point transparent pseudo wire. But this is another option that you could do the transport over layer 3. So in the case that we're doing it over layer 2, which we'll look at later with either Ethernet virtual circuits, VPLS, and EVC, PBB, EVPN. In the case of carrier supporting carrier, this is more complicated because the service provider that is the backbone carrier has to participate in the routing policy of the customer carrier. Basically, the tier 1 ISP is going to have to learn layer 3 routes from the tier 2 ISP in order to provide it transport over the MPLS layer 3 VPN. Now, specifically in terms of the feature and for terminology, we have two new terms, which are the backbone carrier and the customer carrier. What specifically they do is that the backbone carrier is the one that's providing the MPLS layer 3 service to the customer carrier, and it's going to make its forwarding decision based on just the topmost label. And then specifically the device that is connecting from the customer carrier to, or excuse me, from the backbone carrier to the customer carrier, we're going to call this the CSC PE. So it's essentially a provider edge router, but it's one hierarchy up. It's the carrier supporting carrier provider edge. Where the device on the other end, which is going to belong to the customer carrier, we call this the CSC CE. So with the customer carrier, they don't necessarily have to be running MPLS internally, but they do need to be running MPLS on the link that is connecting to the backbone carrier. And we'll see what happens when we don't enable MPLS in that link. What happens is basically traffic is going to get blackholed when it goes through the backbone carrier's core. Now, what we mainly need to focus on is what is going to be this interaction between the CSC PE and the CSC CE. Where the PE side to the CE side is going to be running inside of VRF, just like a normal layer 3 VPN config. What is going to change here, though, is that inside the VRF, we're going to be running MPLS. Now, I had briefly mentioned this before when we looked at some of the L3 VPN documentation of iOS XR, and one of the notes on that document was that XR does not support VRF-aware LDP. So this means that when iOS XR is the CSC PE, there is only one supported design. It has to be running BGP plus label. But we'll also look at this where the CSC PE is iOS, regular iOS, and we'll be doing this with IGP plus LDP. So in iOS, you can do it either way, but in iOS XR, you can only do it one way, which is BGP plus label. On the other side, which is going to be the CSC CE back to the CSC PE, they can be running, or they're not going to be in a VRF, but they do still need to be running MPLS, which means that in iOS XR, we're going to be doing this with BGP plus label. In regular iOS, we can do it either way. Okay, so let's look at this from the logical diagram point of view. So what we're going to be doing is now splitting the network into multiple tiers of connectivity. So we're going to have the customer site that is on router 4 and on router 5. These are the two sites that we're ultimately trying to get connectivity between. So we're going to say that this is CE1 and this is CE2. Okay, then we're going to have the customer carrier, which the customer carrier is going to be made up of XR1 and router 1. But the key is that they're not directly peering with each other. So basically this link doesn't exist here. Okay, neither does this one here. So they're going to be the carrier supporting carrier customer edge, and likewise the CSC CE. And then the CSC PE is going to be XR2, okay, and router 2, CSC PE. So basically we're going to have two separate BGP ASs. There's one that's going to be here, which is the core carrier, okay, core or the backbone carrier. And then XR1 and router 1, these are going to be the customer carrier. Now ultimately, they're running L3 VPN that are going down to the final customer, which is router 4 and router 5. This means that they need to establish regular IP transport in order to run their VPN v4 session. But as we know about VPN v4, VPN v4 has to be going over a labeled path, because otherwise, if we remove the topmost label too soon and we expose a device in the transit path to the VPN label that they don't know, the end result is that traffic is going to get dropped. And we'll see this in the first functional case, and then we'll break some of the config and look at how would we troubleshoot this and why is this a potential problem. Okay, so basically our first step is that we need to run a regular L3 VPN that's going to go between these 5 routers on the right. So router 2, router 3, XR2, XR3, and then router 7. The VRF aware links from their point of view are going to be this interface that's going to XR1 and this interface that's going to router 1. We're going to call this VRF CSC. Okay, carrier supporting carrier. So this is going to be applied on this one and this one, VRF CSC. And ultimately, we just want to test reachability between these two interfaces. Okay, once we get to that point, then we could build the next layer of the hierarchy, which is going to be between XR1 and router 1. Their connections up to their CSC PEs. We'll need to exchange regular IPv4 routing information in order to establish the label path for the VPN v4 session. Then we can form the final VPN v4 session between router 1 and XR1, and then configure the final level of L3 VPN, which is going to be their connections that are down to router 5 and router 4, or router 4 and router 5 respectively. Now, within the scope of the lab exam, though, the thing is that you need to be able to visualize this in the topology first. Who's the core carrier? Who's the customer carrier? Who is the final customer? To figure out who needs to route what particular protocols and what designs are going to be supported. Can we do it with IGP plus LDP, or do we have to do it with BGP plus label? So we'll see that from the link between XR1 and XR2, we're going to be running BGP plus label. The link between router 1 and router 2, we're going to do IGP plus LDP, but this is going to be the VRF aware LDP process from router 2's point of view. Okay, so first step, let's work on building the section on the right, which is going to be between the core carrier. Okay, here we're going to be running OSPF routing. So starting on router 2, let's just look at the show IP route. And essentially the devices are back to a blank configuration where they have just basic IP configured on the links. But there's no routing, there's no MPLS, there's no BGP configured. Okay, if we look at the show IP protocols, basically they should just be running nothing. Okay, so we're going to enable our IGP routing here. So let's look at our interface list, where on router 2 we're going to go in this direction so we can see the traffic transit over router 7, who is going to be our P router. Okay, basically once everything is said and done, I want to look at a packet capture as it's transiting over router 7, and we'll see how that's different from the other captures that we looked at when we were going over just regular layer 3 VPN. Okay, so these diagonal cross connects, those are going to be disabled, as well as this link that's between router 3 and XR3. Okay, so from router 2's point of view, we're going to go to the loopback and run OSPF, IP OSPF1 area 0, and then on gig 1.23. Okay, we're also going to enable LDP. So under router OSPF1, MPLS LDP auto config. Okay, from router 3's point of view, we're doing the same thing. We're enabling on gig 1.23 OSPF, gig 137 is running OSPF, and then under OSPF, we have MPLS LDP auto config. Okay, same thing is going to be true on router 7. So on router 7, we're routing OSPF on gig 1.37 and gig 1.713. And then under OSPF, we have MPLS LDP auto config. Okay, then between the two XR boxes, between XR3, we're going to globally say MPLS LDP, start our OSPF process. On area 0, we're running it on interface gig 00.713 and 1213. And then we have MPLS LDP auto config. Okay, so basically just turning MPLS on globally, and then we're enabling it under the OSPF process. And also I need to advertise the loopback into OSPF because that's going to be the LDP transport source, interface loopback 0. Okay, and I think I missed that on a couple of the other devices, which let me say interface loopback 0, IP OSPF1 area 0, and end. Okay, that needs to be on 2, 3, and 7. Okay, not necessarily because they're tunnel endpoints, but remember when we form an LDP adjacency, the transport source is the loopback. So if I don't have a route to the loopback, I can't establish LDP adjacency. One of the alternate things we could do is to change the transport source to the interface, but the simple solution is just to run OSPF on the loopback. Okay, then finally on XR2, same thing. So globally, MPLS LDP, router OSPF1. Area 0, we're going to have MPLS LDP auto config. And then area 0 is on interface loopback 0 and interface gig 00001213. Okay, once everything is said and done, from XR2, we should be able to show IP route to 2222, and we should be following a labeled path in order to get to that destination. So if we ping to 2222, source is 12, 12, 12, 12, we can reach it, and if we do a trace route, we should see that we are following a label path 13, 7 to 3. There's a question on iOS XR, do we need to configure the address family under LDP? No, you don't need to. If we look at show run MPLS, that's just turning it on globally. If we were enabling LDP on a per link basis, then yes, we would have to enable it under that process. But since I did it under OSPF, show run router OSPF, this just means any link that's running OSPF is also going to run LDP. So you could do it either way. As long as when you look at the show MPLS interfaces, that's really all that we care about, that yes, LDP is enabled on the link. Okay, if we look at the show MPLS forwarding table, the key is that we have a label towards the remote PE's loopback. So this is where we're going to have the VRF. It's going to be on this interface and this interface. So we need to have established a label switch path between router 2 and XR2 to begin with. Okay, so now the basic core is built of the core carrier. Next step is that we're going to configure the VRF, apply it to the interface, then we're going to do the VPN v4 peering between a router 2 and XR2, and then we'll have to do our PE to CE exchange for the routing, or in this case, it's actually the CSC CE to CSC PE routing exchange. But we'll see that from a configuration point of view, there's only going to be one difference here, is that the peering is VRF aware as opposed to being in the global table. Okay, so let's go to XR2, and we're going to create our VRF. Okay, so we'll say that this is VRF CSC. The address family is IPv4 unicast, and we need to configure our route target import and export policy. So we'll say import route target is 1.1. Okay, export route target 1.1. Target is 1.1. Okay, then we'll run BGP1. VRF is CSC, and we give it a route distinguisher. We'll say, just for simplicity, 1.1. Okay, so up to this point, there's nothing that's different about this config. We just created the VRF, give it the target import and export policy, the route distinguisher, and then we're going to apply it to the interface that goes to the customer. Okay, in this case, the interface is do show run interface gig 0000 1112. So we're going to go to this interface. We say no IPv4 address, no IPv6 address. The VRF is CSC, and then we can reapply the addresses, and then we can commit. Okay, again, the issue here is that if you do this in the wrong order, it'll fail out and say you need to delete the addresses first. So you can either do it as one commit or multiple ones. In this case, this is how you would do it if you want to do it just as one single commit. Okay, if we then look at the show route for VRF CSC, and let's make sure we can reach the customer. So ping in VRF CSC 10.11.12.11. Okay, so on router 2, same type of logic. We're going to create the VRF. Let's say VRF definition is CSC. Our route distinguisher is going to be 1.1. Route target is both 1.1. Okay, then at the port level, if we do show run interface gig 1.12, we'll say the VRF forwarding is CSC, and then we're reapplying our IP addresses. The interface is linked to a VRF enable IPv4 on the VRF. So let's say under VRF definition CSC, address families will enable both v4 and v6. Okay, then at the link level, we have VRF forwarding CSC and apply the IPs. Okay, if we show IP route VRF CSC, we should see the customer's link in there, and then we should be able to ping them. Ping 10.121 in VRF CSC. Okay, so now we have the VRF configured towards the customer. We're going to do a VPN v4 peering within the core carrier, and then we'll ultimately need to redistribute between our routing protocols. Now, on the link that is connecting the two XRs, we're going to be doing BGP plus label, where on the ones that are between iOS, we're going to be doing IGP plus LDP. Now, as I mentioned in the slide, iOS XR does not support VRF aware LDP, but if you had iOS XR as the customer carrier, the CSC CE, you could be running IGP on that, or no, actually no, you cannot run IGP because you need to run, yes, I'm sorry, you can run IGP because it's not VRF aware. The key is that from the customer's point of view, this link here is not in a VRF. This link here is in the VRF. Okay, same on the other side. So the VRF is here and here. It's not a VRF on the CSC CE side. It's in the global routing table from their point of view. So even though we're doing BGP plus label here, the reason why we're doing it is because the provider edge router is running XR. If the provider edge router was iOS, the customer edge could be XR, because in that case, it's not a VRF aware process. It's just regular LDP. But point is, there's no VRF aware LDP in XR. Okay, so next we're going to do our BGP peering. Under BGP1, we'll say no BGP default IPv4 unicast. And the neighbor is going to be 12.12.12.12. Okay, they're in AS1. The update source is the loopback. The address family is going to be VPN. Okay, so nothing special about this. This is just a normal VPN v4 peering. We could have route reflectors. We could have a full mesh of VPN v4. Doesn't really matter as long as we're exchanging the routes. The normal BGP routing rules are going to apply between the CSC PEs. So same is going to be true on XR2. We'll say we have BGP1. The address family globally we're activating is VPN v4 unicast. The neighbor is going to be 2222. Update source is loopback 0. The remote AS is 1, and the address family is VPN v4 unicast. Okay, if we then show BGP VPN v4 unicast summary, we should see that we establish a peering between the CSC PEs. Okay, peering is up. Okay, now we're going to have the routing config from the core carrier to the customer carrier, from the backbone carrier to the customer. So again, between the two XR devices, we're going to be running BGP, but on the CSC PE side, the address family is going to be IPv4 labeled unicast, but inside of a VRF. So the hierarchy is a little bit confusing at first, but once we go through the final verification, it'll make sense why we're putting the specific statements where exactly they're going in BGP hierarchy. Okay, so let's think of this from XR1's point of view. When we look at the show run interface gig 00.00.1112, this interface is in the global table. So this means from BGP's point of view, okay, let's say that this is going to be BGP AS 111. So we'll say we have router BGP 111. We have the neighbor that is going to be 10.11.12.12. That's XR2's address. The remote AS is 1. And the address family is going to be IPv4 labeled unicast. Now, this is an eBGP neighbor, so just like in our other configs, we need to have the routing policy language to allow routes out and then to allow routes in. Okay, so we're going to say the route policy pass is going to go out and it's going to come in. Okay, we still need to create that. Let's show config. We will also need to activate IPv4 unicast under global BGP. Okay, so let's go back to BGP and then say address family is IPv4 unicast. And we need to do label allocation. So we're going to allocate labels for, let's say, everything. Okay, then lastly, we're going to have our route policy. Pass is going to say simply to pass. Okay, so if we look at this output, this is similar to what we saw in the inter-AS option C, that it's a BGP peering that's under the global routing table, and we're enabling the IPv4 labeled unicast AFI. So let's commit the config, and then we're going to see that it's going to be fairly similar on the other side, but where the place in the hierarchy is going to be a little bit different. So on XR2, if we look at the show run router BGP, we need to think about what routing table do I need to establish the TCP transport in. So from XR2, when we go to ping 10.11.12.11, that's not in the global table. Okay, we can see it's unreachable. Where this is in VRF CSC. This means that from a BGP hierarchy point of view, the neighbor statement needs to go under the VRF, because that's telling us when we establish the TCP session, what routing table do you need to source it from? I need to source it from VRF CSC. So we're going to go to router BGP1. VRF is CSC. The neighbor is going to be 10.11.12.11. The remote AS is 111. The address family is IPv4 labeled unicast. Our route policy pass is going to go out and in. Then we're going to say the route policy pass says to pass. Okay, now if I look at the config, when I go to commit this, it's going to give me an error message, but I want to show what the failure is specifically, and then how that relates to what particular AFIs that we need to enable. So if we commit the config, it should say it's going to fail because of all changes may have been reverted. Okay, so show config fail, but why specifically did it fail? It says BGP detected a warning that the address family has not been initialized. So this means that under BGP, under the VRF, I need to enable address family IPv4 unicast. And if we commit, it accepts it now. So let's say show round router BGP. But the key here is that there's basically 3 separate AFIs that we need to enable. Globally under BGP, it counts as VPN v4 unicast. Under the VRF, it's address family IPv4 unicast. But then to the neighbor, it's essentially VRF aware labeled unicast. So what this now means, one of the key points that I'm missing here, is that under this AFI here, this is where we're going to do the allocation of the labels. So we're going to say under router BGP1, under VRF CSC, under address family IPv4 unicast, we need to allocate labels for, we'll just say for all routes. Okay, now there's another key point here in XR that we looked at in inter-AS option B and inter-AS option C, is that we need to have that static route that goes to the other end. Because we're now using BGP for label switching, and we know that if the next hop is not a /32 route, then we won't be able to actually do the label binding. So if we look at the show BGP VRF CSC IPv4 labeled unicast summary, this is the static route that we would need to configure it for. So we'll say, and this is a key point here, we're going to go under router static, but then under global routing, we need to go under the VRF, because the static route needs to be where we're establishing the TCP session. If we were to look at the show route for VRF CSC, this is where the neighbor exists. So if I were to say under router static that the route is 10.11.12.11/32 via gig 00.00.1112 and save this change under the address family IPv4 unicast and commit. It does allow this, but if we look at the show route IPv4 and the show route VRF CSC IPv4, notice that the static route doesn't appear anywhere, because basically it is in the wrong routing table. Okay, it needs to go under router static and then under the VRF under there. Same as we're doing it under BGP or under OSPF, under EIGRP. You need to specify what routing table first you're referring to for that routing instance. In this case, basically our routing protocol is static routing. So let's say show config rollback changes last one, and let's roll back the config last one change. We're going to go to router static, then we're going to go to VRF CSC. Then under IPv4 unicast, then we're going to configure the route. Okay, so if we now say show route for VRF CSC, okay, now the /32 for the other end is listed there. Okay, if we go to XR1, we're going to have to configure a static route back because we're still using labeled unicast, but the difference is that this one goes in the global table, not in the VRF table. Because from XR1's point of view, this interface here is not in a VRF. But from XR2, that interface is in a VRF. So we're going to say router static, address family is IPv4, And the prefix is 10, 11, 12, 12. 10, 11, 12, 12 / 32 on interface gig 0000.1112. Okay, so if we show route IPv4 static, we have them directly connected. Okay, next let's look at the show BGP IPv4 unicast summary. And actually that should say the AFI is labeled unicast summary. Okay, now the peering is up.